Kristen Gonzalez Vega, and this is AP Physics C, Electricity and Magnetism. We are live every day. I am in Frisco, Texas, and my friend Roger.
Hi, everybody. My name is Roger Siegel, and I also teach physics. I am in Sarasota, Florida.
All right, so we are going to pick up today with some more capacitance. We are going to talk about some different shape of capacitors tonight. We did nice parallel plate capacitors last night. So tonight we are going to do spherical and cylindrical capacitors. So my name again is Kristen Gonzalez Vega, and we have Roger in Florida. And our two objectives today are to use integration techniques to calculate potential difference between 2 points on a line, given the electric field as a function of that position, and then also derive expressions for a cylindrical capacitor or a spherical capacitor in terms of the geometry of the capacitor and fundamental constants. So I kind of wanted to start off with a little review here of what we did last night and kind of our steps. So by now, we have done Gauss's law a million times. We're going to do it a few more times tonight, maybe even a couple more times tomorrow. But Gauss's law is fundamental because we have to have a function for the electric field in order to be able to determine the potential difference or the potential at a point, because the potential difference is related to the field because the potential difference is the negative integral of the electric field with respect to that position. And then we have added on last night that we can then take that potential difference and find the capacitance if we have two conductors. So when we have two conductors and we charge them up to the same charge, that becomes a capacitor. We did those two parallel plate capacitors last night, and we talked mostly about how the geometry of that capacitor affects the capacitance. We said the capacitance was equal to the dielectric constant, which we are just still sticking with air or vacuum for tonight. We will get into different materials tomorrow, times epsilon naught times A over D. So that's set for those parallel plate capacitors. We also talked about how that relates to the amount of charge that can be stored on a capacitor, because the charge and the potential difference are related. That potential difference is equal to Q over C. So we have all these kind of relationships that we were talking about with those plates. If you increase the surface area of the plate, well, that's going to increase the capacitance. And so we can store more charge for the same potential. We also talked about the energy that you could store on the capacitor as well. Okay, so tonight, let's look at another type of capacitor. Okay, so we have a spherical capacitor here. So we have a spherical conductor that has a radius of A on the inside, carries a positive charge, Q. Where is that charge, guys? Remind me again. Remember, it's always on the surface of that conductor. Okay, it is surrounded by a concentric spherical conductor that has a radius of B, inner radius, and outer radius of C. And its charge is negative Q, right? So again, they are equal charges, one positive, one negative. What's going to develop in between there? An electric field. Okay, so first I want to know, though, is how can we say that if we have an R greater than B, really could even be inside here, right? Let's look at that specifically. So if I draw my Gaussian surface on the inside here, okay, anything bigger than that radius of B is going to have an electric field of 0. So going way out to infinity, everywhere in between there, the electric field is 0. So I want you to tell me why. Why even here? Why does it not have to be out to C before it becomes 0? Anything greater than B, why is the electric field 0? What I want to look at is those charges. And if we look at where those charges are residing, we said they're on the surface. So we've got a positive Q, we'll stick with red for now, positive Q on the surface of the inside conductor. And we're going to have a negative Q. Where is that charge going to want to lie? Well, if the inside conductor has a charge of positive Q, those negative charges want to be on the inside surface. So those negative charges are going to be on the inside surface, not on the outside. They want to be close to those positive charges. So if I look at my Gaussian surface here that's enclosing the in-between part there, and if we did Gauss's law, remember Gauss's law is the integral of E dot dA, which equals the Q enclosed over epsilon naught, right? Both those sides are electric flux. If we look at the surface area, that's 4 pi r squared. But if we look at the Q enclosed, well, what's enclosed in my Gaussian surface? It's all of the charge, all of that positive charge and equal amount of negative charge. So my Q enclosed is 0. If my Q enclosed is 0, my electric field is 0. And that's all the way going out forever and ever because we've got that charge, as long as there's nothing else, right? But why is the potential also 0 in all of this region? Well, let's take that infinity spot, right? We know that we can use that reference point that at infinity, the potential is 0. Okay? We also know that the electric field is the slope or the change in potential. So if the electric field is 0 here and the electric field is 0 at infinity, then what's the change, or what does that slope have to be? The change in potential has to be 0 because remember, E, we can say in the grand scheme of things, is delta V over delta X or dV over dx. So if the electric field is 0 everywhere, that means the change in potential is 0. So if it's 0 at infinity, what does it also have to be up here? It's also got to be 0. It is constant. That's different than we looked at what inside a conductor is, right? If I just had one conductor that's positive charge, and that positive charge is again on the surface, well, the electric field everywhere is 0 inside because there's no Q enclosed, but there was potential inside. Remember, it's a constant potential everywhere in there. Okay, so let's move on here. Let's look then at when we are in the region in between. Clear this out and give us some room. So when we are in between the two plates, in between A and B, what is the electric field? We've done this a million times. I'm going to go through it pretty quick here. Still going to write Gauss though, because we always should. It's a sphere, so Gaussian surface is a sphere also. I'm now enclosing just that inner Q. So if we rearrange, we get that E is equal to Q over 4 pi epsilon naught r squared, which we could also write 1 over 4 pi epsilon naught is K. You could leave it like this, or you could also say this is KQ over r squared. Sounds really familiar, right? Okay, now let's use this then to determine what the potential difference is between the two. So from here to here, what is the potential difference? Okay, let's remind ourselves our E is KQ over r squared, or Q over 4 pi epsilon naught r squared. And how do we get from field to potential difference? Well, we know the potential difference is the negative integral of the electric field with respect to that distance. So here's where we want to be careful about where we're saying like to and from and comparing the 2 points. So you can either go, I always say, let's always work ourselves outside in, right? But we could stay from here to here, but we're going to say that our final position, delta V, but we don't really, oops, I didn't put V here. We can leave this as delta V because I want the potential difference. Now, if I wanted it to know what it was right at point A or right at point B, then I'd have to turn this into like V at A minus V at B. But since I just want the potential difference, I can leave that. Okay, so what we need to look at then is what are the limits on my integration here? Well, I'm integrating from B to A. Right, initial conditions, we know it's 0 at infinity, so we always kind of work our way back in from that infinity. And my electric field is KQ over r squared. Okay, well, what is the integral KQ or constant? We can pull those out. So really we're just taking the integral of 1 over r squared, which becomes negative 1 over r. So my negatives are going to cancel out. My delta V will equal then KQ over r from B to A, which when we plug it in, we get KQ over A minus KQ over B, which we can simplify to KQ times 1 over A minus 1 over B. So that's our potential difference between the two shells. Okay. And then lastly, we can take this one step further. We can find the capacitance. And we kind of started this at the end of last night. We can relate capacitance and potential because the potential difference is the amount of charge divided by the capacitance. So C is equal to Q over delta V. So the charge on one of those is Q, and my delta V is KQ times 1 over A minus 1 over B. What do you notice happens to Q? Cancels. And so we get our final answer, which is our 1 over K times 1 over A minus 1 over B. Sorry, it's a little bit messy for our capacitance. Okay, so we start with Gauss's law. We derive the electric field in the space between our capacitor, no matter what shape it is. We then use our integration of that electric field to get the potential difference, and then we use our relationship between potential and charge to get the capacitance. Okay, so I'm going to give it back over to Roger. He's going to do a couple more examples for us.
All right, great. Thanks, Kristen. All right, so let's go ahead and figure out how we're going to apply this. And, you know, that's how we always really fit our knowledge in new ways as we try and solve problems. So let's go ahead and see what we've got here. So in this problem, tonight we're doing the cylindrical capacitor. And so we've got this capacitor radius A on the inside, this space in the middle, and then another shell on the outside. So this is our coaxial cylindrical capacitor. And our length is L along this way. Now, an important piece that they'll say here is ignore edge effects. And so that means that we can pretend, similar to a way in a mechanics problem when we say assume frictionless surface. Well, we know that's a rare surface indeed. In this same way, we can ignore these edge effects in this class. And as you move up into electrical engineering or into electric physics, you will take a different approach. But we're going to ignore these edge effects. It makes it an easier problem to do. What that means is all of my electric field lines, if I can imagine I'm looking straight down the barrel of this coaxial conductor, all of my electric field lines are perfectly radial between from one electrode to the other, from the outside or inside to the outside. That's my electric field lines. And there's no electric field lines sneaking out. If I look at it on the side, there's no electric field lines sneaking out here that we have to worry about, no edges. All right, so it says write an expression for the electric field for the region between A and B in here. And so let's go ahead and we're going to draw our Gaussian surface as we do. And if you recall, there's some Gaussian surfaces that are going to show up again and again and again. One of them's a sphere, one of them's a cylinder. And so here we are with a cylinder. And I hope you recall that when we do a cylinder, what we are looking at is our surface is like this. And we're looking at this area, the area of this part of the cylinder. And so what is that area? Well, that's a big rectangle. Remember, if we think about our cylinder as the net diagram here, here's our cylinder. And this is the radius of our cylinder. And this is the length L. And so this length from here is the circumference 2 pi r. So to find the electric field, we're going to use Gauss's law. The closed surface integral of E dot dA is equal to the charge enclosed by that Gaussian surface divided by the constant epsilon naught. And so we have that E, since it's constant everywhere along this Gaussian surface, everywhere along here, my Gaussian surface, the E field is constant, it can come out, and then I'm going to have the closed surface integral of dA. And my charge enclosed is just Q, that's given in the problem, and again, the constant epsilon naught. Now, looking at this, if I add up all this area, what is this area? Well, this area is 2 pi RL. So that's 2 pi RL. And so this is going to be is equal to Q over epsilon naught. So what I'm going to get finally here is E is equal to Q over 2 pi RL epsilon naught. And so that is our electric field in this region. Now, the next cut for us, the next thing to do is to determine the potential difference in that area. And so let's go ahead and do that. And so, I'm sorry, I said the potential difference in the area. I want to use that word difference. We're always thinking of the potential difference. And so if we say the potential difference between the cylinder and the shell, we mean compared to at infinity, the potential difference from infinity out to the to this point here in the shell. And so what we're going to do is we're going to use our definition of potential difference. We can't just say that V is equal to ED or E times distance. We can't say that because this is not a uniform electric field. So we're going to have to add up. This is negative E dot dr. And we're coming from infinity all the way to this point. I'm sorry, we want to know, well, let's go ahead. Yeah, we're coming from infinity. I don't want to go from infinity because earlier what we had learned is since when we're out here, we're enclosing a charge of 0, then my potential difference doesn't start until I get to, to here. So I can go from B, from infinity to B is 0, and then from B to A. And so that's what we want to find out in the shell. And so what we have then is we have Q over 2 pi RL epsilon naught times dr going from B to A. And so that's going to be, and that's a negative. And so when we do this, the Q comes out. Let's change actually the negative to a positive. And so let's go from A to B of Q over 2 pi RL epsilon naught dr. Now, the only thing that is a constant, that's not a constant, is R. Everything else comes out front. So that's going to be Q over 2 pi L epsilon naught integral of dr over r from A to B. And so that becomes Q over 2 pi L epsilon naught natural logarithm of r from A to B, or Q ln B over A 2 pi L epsilon naught. Well, that was a long way to go, but that gave us now the potential difference between this plate and this plate. All right. Now let's go ahead and determine the capacitance. And this is the easier part. We know that C is always equal to Q over delta V. And so the Q is, that's our charge on both plates, either plate, over Q ln B over A time divided by 2 pi L epsilon naught. And so what we can see is the Q's cancel. And so we get 2 pi L epsilon naught over ln of B over A. And so that's our capacitance for our cylindrical capacitor. Now, I don't know about you. I think that's pretty cool that we can do that. I want you to give yourself a pat on the back for being able to do that derivation. And if you can't do it, you're going to have to rewind the video and give it a try, because it's a good one. All right, so let's go ahead and come back to our next piece here. And that's going to be right down here, cross section. Now we've got spheres. And so the cross section of two concentric spherical metal shells is shown. So we've got one sphere inside another sphere. They have concentric, they have the same center. Let's go ahead and give the outer shell, again, a radius of B. We won't worry about units. And the inner shell will be a radius of A. We won't worry about units. And the Q plus will be 1 nanocoulomb. That's fine. And sometimes, by the way, sometimes AP will show this support in here. Sometimes they won't. They'll just draw 2 circles and they'll say inside sphere, outside sphere. Don't worry about it if you don't see a support. Just know that physics teachers can make things appear and disappear just like that by drawing them. That's the fun of doing it. Okay, so let's go ahead and find the potential difference between the shells. Well, again, I'm going to have to find the electric field to be able to find the potential difference. All right. So again, I know that I've got Q on the inside sphere and Q negative on the outside sphere. But once again, my E field is going to be by Gauss's law. So we're going to have E dot dA is equal to Q enclosed over epsilon naught. And I'm going to integrate all over this sphere, my Gaussian sphere. And so again, because of a constant E, I can pull it out front. And then I can say, well, that my charge is my charge. And so E times, and the surface area of a sphere is 4 pi r squared is equal to Q over epsilon naught. And so what we get is E is equal to Q over 4 pi epsilon naught r squared. Ladies and gentlemen, that is the same as E is equal to KQ over r squared. So this is what we have. Again, since it's a sphere and we're outside of this charge, we don't care about any of the charge that's on the outer sphere, just on the inner sphere. We only have to worry about that enclosed charge, and so it acts like a point charge. Now, what's the potential difference? Well, we're going to go now we're going to integrate from B to A of negative E dot dr. And so that's the negative integral of K Q over r squared dr from B to A. Now that's going to give us the negative integral. Let me go ahead and pull out the Q and the K. That's KQ times negative KQ times the integral of dr over r squared. And again, from B to A, that is going to be negative KQ times a negative 1 over R from B to A. Now we have a negative and a negative, so that's going to be a positive. So we get KQ times 1 over A minus 1 over B. And so that is our voltage difference from B to A as I go in that direction. KQ times 1 over A minus 1 over B. Now, I want to clean it up a little bit because let's see. Well, no, that's okay. We'll leave that there. Now, the last thing I'm going to do tonight is I'm going to find the capacitance between these two. And so once again, now this is the easy part. C is equal to Q over delta V. And so the Q is again Q. That's the charge on each plate. And the delta V is what I have over here. So that's going to be KQ times 1 over A minus 1 over B. And if this were the exam, I'd probably walk away from the problem now, but I, as a teacher, am loath to leave a compound fraction. And I think it's important to finish it. So let me go ahead and finish it for us. And so this Q cancels. And so what we have then is we have 1 over K, and I'm going to get a common denominator here. I'm going to get a B over AB minus an A over AB. And so that means we have 1 over K, and we have B minus A over AB. And so my final answer is C is equal to AB over K times B minus A. And notice that the sign works out to be positive, which is what we would look for the capacitance. So that means we had all of our directions correct. All right. I challenge you to do that problem, to rewind it and try it yourself, work through it. It's a great problem to really get these ideas solidified into what we're getting at here. So I know that Kristen's got a good one for you next, and keep working hard.
All right, thanks, Roger. Yeah, we got one more thing tonight, and it's going to seem repetitive, but it's a little bit of a different view on the same kind of problem. And I'm going to give you some time. I'm going to kind of pause and let you, since we have some time tonight, let you work through this now that we've done a couple practice. Now I would like you to kind of work along. So we have an isolated conducting solid sphere of radius A shown above that is charged to a potential of V. So we want to first determine what the charge on that one isolated conducting solid sphere is. Okay, and then we're going to hook up two shells and connect them together surrounding it. So they're brought up without contacting the solid sphere and connected to form a spherical shell surrounding and concentric with the solid sphere. The outer shell is then grounded. By means of Gauss's law, determine the electric field in the space between. Okay, so I'm going to give you a few minutes and mute myself here, and I would like you to work those two parts for me. Determine what the charge on that sphere is, and use Gauss's law to determine what the electric field between the two is. So ask yourself, what is that? And also, what is this grounding going to do? We haven't really talked about grounds too much. So what would happen when we ground that outer one and then find the fields? Okay, if you need some more time, you can pause and wait till you're done, but let's talk about these two. So part A, we know it's charged to a potential of V, and we know the radius is A, so let's find the charge. So if the potential is V, and we know that the relationship once we get here is that V is equal to KQ over R, then we can say really this is KQ over A is equal to V. And let's rearrange and solve for Q. If we do that, we get that Q will be equal to V times A over K. So that's our charge on that. Okay, so then if we connect up this outside shell here and we ground it, what's that going to do? We talked a little bit about grounds with charging and with our electroscopes and things. So what does introducing a ground do? Remember, it allows for charge electrons to flow either into or out of our conductor. So which one of those two things do you think you will want to happen? Well, the negative charges want to flow into our conductor or out of our conductor? Well, if this one has a positive charge, then we'd want to have negative charge. So there would be now negative charge, equal amounts. So our inside sphere has a charge of V times A over K, and our outside sphere will have a charge of negative V. A over K. Okay, so then let's use Gauss's law. Not that you had to do that to do Gauss's law, but conceptually we want to be thinking about what's going on. So if I use my Gaussian surface, we do Gauss's law. It's going to be the same way we do it always. We're just dealing here with a little bit of different variables, a little bit of a different scenario. Q enclosed over epsilon naught, still a sphere. But we're going to plug in for our Q enclosed that our Q enclosed is V times A over K, still times our epsilon naught. Okay, well, if we divide by our 4 pi r squared, then we get that E is equal to V times A over 4 pi epsilon naught times K times r squared. And if you recognize what is 1 over 4 pi epsilon naught equal to, that's K. So really we get K over K, and our K's are going to cancel. So really the field becomes V times A over r squared. Is that what you guys got? Okay, we're going to move along. Now I want you to find what the potential of the solid sphere is relative to the ground and the capacitance of the system. Okay, so again, I'm going to give you a couple more minutes. Find the potential of the solid sphere and determine the capacitance. Okay, if you need more time, again, go ahead and pause, but let's look at it. Let's find that potential difference. So we want to find that integral, that negative integral of the electric field. So if we plug in then that our electric field was VA over R squared, well, we can pull out that V and that A. Really, we're just integrating that R. So we get delta V equals V times A over R from A to B. So if we plug that in, we get VA over A minus VA over B. So if we cancel out those A's, if we multiply to get a common denominator, then we get V times B over B minus V times A over B. So really, we get V times B minus A over B. And then lastly, we can get the capacitance. How do we get the capacitance, guys? Capacitance is going to be equal to our Q over our delta V. So we got to go back to what our Q is, right? We don't want to leave it as Q because we already solved for Q back in the beginning. Q was V times A over K. So we get V times A over K divided by our potential, which is V times B minus A over B, I'm going to multiply by the reciprocal just to simplify this for us. So this becomes B over V times B minus A. Okay, and when we simplify that down, we can cancel out. And we end up with A times B over K times B minus A. So process was the same, just a little bit different variables there. So we have done lots and lots with putting all these things together, right? Doing Gauss's law to find the field, using the integral to find the potential difference, plugging in to get the capacitance. What we're going to talk about tomorrow is what happens if I take a different material. And let's fill in maybe this bottom half of my capacitor with this different material that has a different dielectric constant than air. And we want to look at what's going to happen to that capacitance now of that capacitor. So we're going to look at what we call dielectrics tomorrow and how that affects our capacitance, our energy, our charge stored within our capacitor, and all of that. So Roger, anything you want to add or anything you want to say to wrap up tonight?
Yeah, thanks, Kristen. Just thanks for tuning in and working so hard. You know, don't be discouraged if these problems seem hard, because they seem hard to us too, and we're working, you know, to understand them. So please keep working hard, and can't wait to see you next time.
Okay, come back tomorrow.